As we know, to enhance the overall performance of a computer system, several processes must be executed concurrently, which implies that several processes must be kept in memory simultaneously. Memory must be shared, which immediately brings to the picture the question of management of memory, and that will be the topic of our discussion today. We'll discuss how the main memory is managed and shared amongst different processes. To start the entire discussion, let us first start with the problems that is associated with the memory management. Okay, let's see. The memory management is the topic of discussion today. Here, in this plate, I have tried to show that what are the steps associated with the translation of source program and then ultimately executing it. Here is a source program. It may be a C language program, which has to be translated by the compiler into the object module. The source program may be an assembly language program also, which will be translated by an assembler into an object module. There may be more than one object modules, okay, that has been translated separately and had been kept separately, but they are now to be linked together if they are to be linked by means of a linkage editor to create a load module. Now, the purpose of the linkage editor is that there may be inter-object references. That means there may be a symbolic address, say XY here, which has been referenced from here. For example, it may be a jump subroutine to a subroutine XY in this module. Now, this inter-reference between object module are to be resolved by means of the linkage editor, and then a complete load module is generated here. Now, this load module and the system library are to be loaded by means of the loader into the memory, and we call it a binary image which will be executed in the memory. Now, there are several problems associated with the thing. Firstly, when we are writing a source program, we are basically using symbolic references like XY, AB, etc. The compiler, while translating these instructions where the symbolic references are there, the symbolic references have to be changed into address locations. We call it binding of an address to a symbolic reference. Now, since the compiler doesn't know actually in the memory ultimately where that module is going to be loaded, okay, the compiler cannot bind the absolute addresses to these symbolic references. Okay, therefore, what the compiler does is that it uses a relocatable address. That means an address which is in terms of a displacement with some origin, and this origin is generally the beginning of the program. Now, the purpose of the loader has to be to change this relocatable address to that absolute address where that particular variable is going to be loaded into the physical memory. Okay, let us see by means of an example. Let me try to clarify. Okay, say here, assume that we have. Let me not look at the right hand side right now. Say a statement y equal to y plus z. It may be a C language statement. Y, z are all symbolic references. Now assume that it has been translated into an assembly language program. It has started from 000 location in hex. Okay, this is address shown in green, right? Assume that add yz, okay, is the translation of yz by means of a two address machine, which means that z is added to y and the result goes into the y. That is what has been done over here. That particular instruction has been assembled starting from the location 0100 with reference to the start of the assembly language program, right? Which the assembler will translate into this, okay, into add 510 to 512, okay, where 5100 510 is the address location of y given a relocatable address starting from the beginning of this program, and 512 is a relocatable address of Z starting from the beginning of this program. Now, for this will be ultimately the translated version as done by the translator using two relocatable addresses 510, 512 from the beginning of this particular program, okay, which is assumed to be always 0, 0, 0, 0, okay. Now, say while executing this program, the memory location that is available is not from 0, 0, 0, but from say 1, 0, 0, 0. In that case, you can see that if we keep the instruction as such, that means add 510 to 512 and load that entire program starting from 1000, the execution of the program will be wrong because the addresses that is bound to the variable y should be 1510 and to variable z should be 1512 and not 510 and 512. Now, if we do not change these two addresses, as we have shifted the entire program from 0 to 1000, okay, in that case, while executing add instruction, it will go to the memory location 510 and 512 for the data, whereas data is actually in the location now in 1510 and 1512. Therefore, this binding of symbolic addresses by the compiler is relocatable, and the changing of these relocatable addresses, that means the binding of these relocatable addresses to absolute addresses, should be done by means of the loader while loading this program into the physical memory, depending upon from where the program is going to be loaded. Okay. This is quite fine as far as the loader knows that actually from where the program is going to be loaded, and finally the program is kept there for execution. Now let me try to give few more examples, okay, to clarify this issue. Suppose that we have a instructions to move R1, R2. That means content of R2 I am moving to R1. You see here that here, since no memory references is involved, okay, while executing this instruction, right, therefore the code that is generated is absolute, because if we move these particular instructions from any location to any location, right, the execution of this instruction is not affected because no memory reference has to be done. Therefore, we say that no relocation is necessary for this particular instruction. Okay. Let me try to give another example. Right. Here we have a source code. Right. Once more, I have written in assembly language. Say move direct addressing. That means content of memory location XS should be moved to R1, and say the compiler has bound the address, okay, 1000 to the memory location XX. Here, side by side, I have shown the translation from this assembly language. So to say that machine language partly. Here you see that move R1 XX will be ultimately broken down into two words. One should contain that move, the register assignment, and the same shows basically that it's a memory reference, direct memory reference. And since XX has been bound at the compile time to location 1000, okay, that at location 1000 I have kept 133, the content of X. Right. Now you see this once more is a relocatable address with respect to 000. Now if we move this, right, to say entire program to, instead of 000 to 7000, then all these addresses will change to 7000 onwards, and you see that instruction execution, if we do not change this particular word in this program, will be wrong. Therefore, this is a relocatable value, But this is an absolute value because this need not change if I want to change the entire program, slide this entire program anywhere into memory. This therefore should be changed to 7000, okay, in the case of my direct addressing. But now assume that I am using relative addressing, PC relative addressing. In that case, when this particular instructions will be executed, right, program counter will be pointing to this when this memory location is being referenced, okay, being accessed. Now, in the case of a PC relative addressing, as we know, that instead of that 1000 here, we give the difference between the target and the content of program counter at this point. That means we should keep, so originally 1000 minus 0500, which is B00, is the displacement. Therefore, if we keep, in the case of a PC relative addressing 0B00 at the location 745E, then at the time of execution, what the CPU will do, it will take 0B00, add with the value of the program counter, which will be 0500 originally, and we will get the address 1000, which will be the address of the operand. But now, say if we shift this entire program from starting from 7000 also, then this displacement at this location, that is 0B00, remains unaltered. That means the displacement from of the operand address from the present value of the program counter, which is 0B00, remains unaltered, and in that case the content of this particular word is also absolute, which means the advantage of a PC relative addressing is that even if we shift the entire program anywhere in the memory, the addressing scheme, the addressing mechanism allows us, okay, the advantage that we don't have to relocate that particular word in the program. Anyway, now in general, what the situation is that whenever we are trying to load a load module into the memory, okay, that address relocations of the entire program has to be done. Now, the problem is that if the loader knows that from a particular location that program is going to be loaded, then the loader can take that program, that object module, where the informations of relocating the different words in that object modules are kept in that object module itself. Loader can take these informations along with that object module and relocate that entire program and can put into the memory for execution. But say after some time, due to reasons of efficiency, that entire program is shifted or is required to be shifted from one place of the memory to another place. In that case, that entire relocation has to be done, and which is essentially extremely time consuming and a complicated process. Therefore, something has to be done that we do not have to all the time relocate the program as we move the program from one portion of the memory to other portions of the memory. Okay, either at the load time or even at the execution time, as long as we have the information starting from which location the program is going to be loaded. Okay, this is the scheme that has been shown here. Okay, here you see, as we have the CPU, right, the CPU generates a logical address. By that I mean, okay, if we come back to this slide, this we call the logical address space. Okay, right, and when we map this entire program into the physical locations, say starting from somewhere other than 000 into actual physical memory, we call this the physical address, right? Now, this is a logical address space. Sometimes we call it virtual address space, and the CPU will generate this logical address. Okay, that means it will always generate 510, 512 in place of 1510 or 1512. Okay, depending upon where that instruction, where the program has been loaded. Therefore, the CPU will always generate the logical addresses that has been kept in the logical address space of the program. Right? CPU will generate 510, 512. We keep, as CPU generates a logical address, we keep a memory management unit. MMU is a memory management unit which will map this logical address into physical address where that particular memory has been relocated, particular address has been relocated. That means the CPU will generate 510, 512. That memory management unit will generate 1510 and 1512. Okay. And to generate this 1510 and 1512, the memory management unit has to be given the information that this particular object module or this particular image module, binary image module, has been loaded from the locations 1000. This is load location of this particular module, right? Now, if we can do this, that means if we can supply the memory management unit with that information from where, okay, a particular program or the process has been loaded, okay, say 100, this information I give it, then the memory management unit should be able to generate the physical address, okay, from the logical address. Therefore, essentially, the memory management unit does a mapping function from the logical address to the physical address. Okay. Now, this is what the basic purpose of a memory management unit is, and naturally, the details of a memory management unit will change depending upon how we want to see the logical address and how we want to generate the physical address. What is the mapping involved from the logical address to the physical address, and how we want to see the logical address as such. Okay. Now, first thing that we'll be doing is that we'll assume that our total module will be kept in the physical memory in contiguous memory locations. Okay, that means it will be in successive memory locations beginning from the start of the program process to the end of the process. Now, let me just clarify one point, that during this few lectures, I will use the term that process, the program, and the job interchangeably, where there is no confusion of the meaning. Right. Now, if we assume now that the program will be kept in the memory in contiguous memory location, right, then what we'll have to do naturally, as I have shown here, that we'll have to use a partition of the memory. Okay, this I call a partition. We have to keep a partition of the memory. We have to use a partition of the memory to load the program. Okay. Now, first our first method of our memory management unit will be that partitioning memory management scheme. Here I have shown a contiguous allocation, and I have shown a single partition. That means in the memory, only one process has been kept. Okay. Let's say and in a contiguous memory location, starting from some starting address to the end address. Okay. Now, once say here the CPU, as this program will be executed, process will be executed, the CPU will generate anytime a logical address. That may be the logical address of an instruction. It may be the logical address of any data. Now, here in this scheme, we keep what we call a limit register. Okay. The limit register value is set to here. Say this is the value of the limit registers L, right? Whatever the address that is generated, logical address that is generated, okay, first it says that whether it is less than the value of the limit register or not. Okay, since it is logical address, this L is not the actual physical address in here. This L is the, I should clarify, this L is the end of the logical address. Okay, that means if the program ends here, say at the location say 0800, okay, then this is L, right? Therefore, first checks this logical address whether it is less than the then limit register or not. A limit register is kept where this value is loaded just to check that whether you are going beyond your partition or not. If this program is going beyond the partition or not. If it is not, that means it's not less than the limit register where the value of L has been kept, then an address error is generated. That means you are violating the address of your space, of the logical address space, and an address error is generated. A trap is generated, and immediately the operating system takes hold of it and takes care of the situation. Then an address violation has taken place. Okay. But if it is less, that means no address violation has been done. In that case, a relocation register is here, right? In the relocation register, say this is R, that value is kept here. That means where this object module has been loaded, the starting of this address, the starting of that object module, that is the module, has been kept, will be kept in the relocation register. Once more, let me tell that I have almost interchangeably used the term, this object module and that image, binary image module. What I exactly will be meaning is a program in the form that is executable and kept in the memory. Okay. Now, this relocation register value R now is then added with the logical address to generate the physical address. You see here, if 1000 I keep, so if this 1000, which is that relocation register value I keep over here, and if I generate the address by adding the logical address with this relocation register address, this physical address, in that case, I will be generating the actual addresses of the variables y and z. Okay, this is the script that is employed over to here. That means that relocation register value is to be added with the logical address to get the physical address. Okay. Now, this way, you see that we solve the problem of logical address to physical address mapping. This, in fact, is the purpose of that MMU. Now, for this memory management unit, this partitioning memory management unit uses two registers. One is the limit register, which takes care of whether the address that is generated goes beyond the logical address space or not, and a relocation register. In the case of the relocation register, the value of the relocation register is always added with any logical address that is generated to ultimately come to the physical address. Okay. Now, this is a single partition that we have used here. Naturally, if we have to give more programs, several programs in the memory, right, we cannot have the single partitioning scheme. We'll have to have the multiple partitioning scheme. Right? Because in different partitions, different processes will be loaded. Okay, let us see what happens in the case of a multiple partitioning scheme. Now, one important thing that I should mention here, let's say if this partition, right, is shifted in the memory anywhere. So, for example, instead of this place, which is originally say 1000, I want to shift to, say, for example, starting from 5000. What I'll have to do is that I'll have to load the relocation registers with the value 5000. Right? Therefore, as if even during execution time, if I want to shift this module from anywhere to anywhere, where I am shifting to, that particular address has to be known, and the operating systems, before starting the execution, resuming the execution of this program, has to load the relocation register with the starting value of that particular partition in that main memory. Okay. Therefore, let us see that what we have learned. We said that we have learned what is our logical address space, the address space that is seen by the central processing unit, the CPU. We call sometimes the virtual address. These two terms I shall be using interchangeably. And the physical address is as seen by the memory unit, Therefore, this is the physical address is as seen by the memory unit. Okay, with this, let me now go to that contiguous allocation. What happens in the case of a multiple fixed partitioning scheme, right? In the case of a multiple fixed partitioning scheme, since we'll have to support more than several processes, what we do is that entire memory, this is a physical memory, is divided into several partitions. Say 50K here, 50K here, 100K here, 200K, 200, 500K. Okay. This partitioning has to be done with some prior knowledge as to that the sizes of the different programs that generally is handled by means of this computer system. Okay. Here I have assumed that the programs of sizes 50K and of 200K comes more frequently than programs of sizes 100K or 500K. Okay, and therefore two partitions have been kept of 50K and 50K, one of 100K, two of 200K, and one of 500K. Now this is a policy decision the system administrator has to take and accordingly define the partitions. Right. Now, as a process comes, depending upon the size of the process, a particular partition is allocated to that process. Say, for example, a process comes which is less than 50K. Say this is a partition. Say this is allocated to this process. Right. Say another comes which is more than 50K but less than 100K. Okay, that means we go by best fit. We take this 100K and say possibly load this program here. Another program of 400K comes, we load this program here. Okay. Say another program of 150K has come, we load the program here. Now you see, as we have loaded the program, one important thing that you should note that naturally no program or process will exactly fit a partition, and therefore there will be some holes, we call them holes, okay, right? And the entire memory will, in that case, will have some fragmentations. That means here we call this particular hole the dividing of this entire memory space into occupied spaces and holes. So, for example, another program has come, we have kept it here. And in this case, another program has come, so we have kept it here, right? Now you see that entire memory has been divided into some occupied spaces and some holes. This is, we call that fragmentation. That means fragmentations of that entire memory into several holes, which right at this moment cannot be utilized, okay? Because we have made fixed partitions, and the programs that has been fitted into this partition doesn't occupy that entire memory, entire partition space. Holes are generated, that memory has been fragmented into holes which are distributed, strewn all over the memory. Now let us come to the mapping part, memory management part. Now this entire, all the programs will now be executing concurrently, either in apparent or real concurrency. Now, whatever is the situation, whenever a program, say this program is being executed, right, its corresponding relocation address and the limit value, okay, are to be loaded into the limit register and the relocation register. That means the relocation value, that means starting value should be kept in the relocation register and the limit value should be kept in the limit register. Now, as we switch from process to process, okay, for multiprogramming, the limit registers and the relocation registers should be accordingly switched. Therefore, somewhere the operating system should keep all the informations of all the limit registers and the relocation registers of the different processes. That has to be kept in a table. Whenever that process is switched, that means the operating system switched from one process to another, the corresponding relocation register value and the limit register value are to be loaded into the relocation register and the limit registers so that the processes can operate smoothly, okay, without error. Now, what will happen is this: so sometimes naturally one of these processes will be, executions will be over. In that case, another process should be brought into this partition. Its corresponding relocation and the limit values are to be kept in the table. Right. This way, as the process is finished or completed, the process is withdrawn, the memory space is declared free, another process is brought into this particular memory space, which is big enough to fit in. Okay, we go for the best fit, that means the smallest partition that can hold this particular program. That's the way generally in this fixed partitioning method we go. But to keep this, the jobs can be kept, in a queue. Say these are the jobs that are coming, we keep in a queue, right? And as a partition becomes free, the corresponding job which can be fit into this partition can be taken from here and loaded into the memory. Okay, either a single queue can be kept, or instead of a single queue, we can keep queues depending upon the sizes. That means one queue for 50K size, one queue for say 100K size, one queue for 200K size, and so on, right? The jobs are here. As the job comes, depending upon its size, it is in fact put into the different queues, right? So that whenever a 50K partition turns out to be free, one can immediately go to the corresponding queue, take a process and load into this partition. Now you can see here the disadvantage of this entire method is very obvious, is that there are many holes that may be created, okay, and this fragmentation technique, this fragmentation process, okay, that means that unused areas, the memory is remaining unutilized for a good fraction of that entire memory. That naturally is a very poor utilization of that entire memory, and that is the disadvantage of this method. Okay. Now let us see, therefore, instead of a fixed partitioning, okay, what we can do. What we can do is we can go multiple dynamic partitioning scheme. Okay, this is our multiple dynamic partitioning. Here, instead of fixed partitions that has been kept like this here, we do not make any fixed partition so far as this technique is concerned. As a process comes, okay, so for example, a process of size 100K has come, we take a partition of say 100K and allocate that portion of the memory, okay, to that particular process. Say this is the process P0, it needs 100K, we have cut out a chunk of the main memory of size 100K and has been allocated to P0, right? Another process say, has come of size, say, 500K. Okay, this is a process P1. We take now a chunk of 500, just starting from here. A chunk of 500K memory location is now taken, right, and is allocated the process P1. That way, say another process comes, say P2 of say 400K, right? So 400K will be taken from memory and is allocated, right? And say, for example, another has come which is, say, 100K once more. Say this process is P3, and another has come, say, P4, which is once more 200K, right? We allocate 200K here, and in this situation, you can see that this amount of memory, that means this amount of memory at the fag end of the total physical memory, a hole has been created, right? And this amount of memory will be wasted. It's not right at this moment. It's not like the situation that several holes are there and a good amount of memory is wasted. Okay. Now that is quite all right. As a program is loaded, the corresponding limit and the relocation values, relocation register values, is kept in an operating system table. When the processor is switched, okay, from one process to another process, the corresponding relocation register value and the limit register value is loaded, and the process is started. Okay, this process is activated. This way, it goes on. Memory wastage is quite small, right? And physical to logical memory mapping will always go by this. Okay, the physical logical address is generated here and the physical address is generated here, and this is done all at the runtime by means of this hardware. Okay, quite fine. But say after some time what happens, you see that say this program P2 is over, but execution is over. Okay, immediately what happens, therefore, you see that another program which is waiting in the queue can be now brought in and put into this partition, right? The partition from here to here now turns out to be free. Okay, a program P2 has completed, or it has been thrown out due to anomalies, okay, due to error situation. In that case, this 400K memory locations will be free, and we can bring another program immediately which can be fed into 400K memory locations. And you see the situation here immediately, that from here to here, P2 is over, and some job, say P5, has been brought in, which does not need the total 400K memory locations. Say it is only of 300K size, right? Say 300K, and you can see immediately that it will take only 300K, these portions of the memory, and there is a hole that is generated, right? Similarly, after some time, say this P0, that process is over, that 100K is free, and a process, say P6, has been brought into this particular partition that has been made free of size 100K, and see this is only 50K, and therefore you can see easily that this is the hole that is generated, which means that after some time, right, after some time, we'll find that this entire memory will once more get fragmented into holes and occupied areas. And the holes will be all streamed over that entire memory location. It may be so happen, therefore, say the situation may be that, say this is a program space, say this is another program space, right? This is say another program space, right? Say this is another program space, and here are the holes that has been generated. Now a new process has come which is bigger than any of the holes that is there, that any of the holes that is in the memory, but is smaller. If we could combine that some of the holes together, in that case the program could have been fit in. In that case, you can see that though we have sufficient memory space so that the program can be executed, okay, there are sufficient free memory spaces, but since they are all distributed, we won't be able to run that program, right? Therefore, what to be done about it? What can be done about it is this, right, that we can try to utilize the entire memory which is free by trying to put all the occupied areas at one place and the free areas at the end of the entire memory space. That means what we say is that if we compact it, compaction means that start pushing all the programs to one side of the memory and create the free areas at the other side of the memory. If we can do it, in that case you can see that possibly up to this is the portion of the program that will be this is the portion of the physical memory that will be occupied by all the processes that are in the memory, and we can create a good amount of free space here, which we can start allocating to the different processes that is coming. Once more, after some time, okay, as the system goes on, system moves on, holes will be created, the memory will be fragmented, and if necessary, we'll once more compact it to create one chunk of free area into the physical memory, so that the more processes can be brought into the picture, right? And you can see one thing, that as the compaction is not much of a problem, okay, as long as we are shifting, we know that from which memory location every program is starting. That means we know the relocation register values and accordingly change the relocation register values in the operating system table. As we shift the programs, the relocation register values are changed. Therefore, as we switch from one program to the other program, there is no problem, because we have basically what I've done, that logical address has been separated out, okay, and has been from the physical address, and the logical address and physical address mapping only involves a relocation register, which values we can keep track of and which value we can change as is needed, right? Therefore, the advantage of the dynamic partitions is immediate, that whenever needed, we can push all the partitions to one side to create free space, which can be very fruitfully utilized, right? Now, the behavior is quite dynamic. For example, when we should compact we can compact at different times. Whenever that, for example, we can compact whenever a new process comes in, okay, right? Or we can compact when we find that we have a process, right, which is small enough and can be accommodated if all the holes can be brought together, only then we compact, right? Therefore, the decision is operating systems, because some overhead is always associated with it. We'll have to move programs from one place to the other place, and we'll have to keep the relocation registers. And during this process, this is essentially overhead, since no application programs is progressing. The operating system is taking care of it, right? this is so far as the utilization of memory is concerned. Another aspect of the utilization of memory is this, that allocation strategy, right? So, for example, since we have several partitions, okay, we have, so for example, let's take this situation that we have many holes here, right? 1, 2, 3, 4 holes, and the process comes. If the process is such that it can be accommodated in more than one holes, which is the hole into which this process is brought in, right? Now, that is an allocation strategy. Now, this allocation strategy can be first fit. That means you start from the beginning of your memory location. Whichever is the hole big enough, okay, to fit that particular process, you put that process into that hole. Okay, this is the first fit algorithm. Another can be the best fit. That means you take the smallest hole big enough, right? If you take the smallest hole big enough, basically what you are generating in the case of best fit is that very small holes, right? For example, this is that if it's the smallest hole big enough to fit a process, the hole that will be generated here, this hole, will be the smallest hole, right? And another can be, this is the best fit, and then the worst fit. That means you take the largest hole, okay, to fit it. The philosophy of that worst fit is this, that if you take the largest hole where it can, for example, if it's the largest hole where can that process can be fit in, say this is the process, and that was the hole, you want to fit it over to here, then a good amount of memory will be available so that it can be allocated to either a number of processes or a big process. Therefore, that is the worst fit. Therefore, our allocation strategies are generally three. One is the first fit, second is the best fit, and third is the worst fit. Okay, all of them have been tried, but it has been seen that the storage utilization is better in the first fit and the best fit. Okay, this is the places, this is the strategies where the storage allocations are better, right? Now, therefore, you see that two things are involved over to here so far as allocation strategies are concerned. That when you have fragments, okay, when you have holes, when a new process comes, where it goes. And another is that when a process comes, you do not have a hole big enough to accommodate it, but you have holes, the summation of which is big enough to accommodate that process, right? In that case, you should go for compaction. Okay. Now, how do we keep track of how the memory management unit of the operating system keeps track of the holes and the occupied areas? Naturally, you can keep a linked list of blocks. Each block is having the information of the start address and that end address of an occupied area or a hole, okay, or unoccupied area. These two linked lists, the data structure, the memory management unit of the operating systems will always consult to decide about when and how to fit, okay, give a allocation of memory, or when and how to compact. That's all for this lecture. We shall discuss other methods of memory management in the subsequent lectures. Thank you.